So in this video, we're going to take a look at what's commonly called Hess's Law, and it is a method for adding up heats of formation or Gibbs free energies of formation to be able to get heats of reaction for things like this. This, for example, is the reaction of anhydrite plus water, 2 units of water, to give us 1 unit of the mineral gypsum. And here in gypsum, the .2H2O means we have 2 molecules of water attached to the calcium sulfate component to make this mineral gypsum. Now, if we want to know let's say the Gibbs free energy of formation, the Gibbs free energy of reaction for this, or the enthalpy of reaction, we're not going to be able to look this up in tables like Roby et al. 1979. But we can use the tables from Roby et al. 1979, which you can download free from the web if you want to follow along with these values, to be able to calculate this and many other functions. So what we're going to do is take a look at this equation as it exists as a function of 3 equations that involve the formation of anhydrite and water and gypsum from the elements. Now, it's very important to differentiate. Over here, we're looking at gypsum being formed from the elements. So what do we have for there? This enthalpy delta H should have a sub F for formation, and that is formation from the elements, where we take the enthalpy of the formation of gypsum is equal to the enthalpy of gypsum itself minus the reactants. And in this case, the reactants in this table here are the elements. These are always formation from the elements shown here and out of the view in this table here. So the elements in this case would be calcium, we just need 1 of those. The enthalpy of sulfur, we just need 1 of those. We need 3 enthalpy units of oxygen gas, and then 2 enthalpy units of hydrogen gas, right? So that'll give us the Ca, SO4, and then 2H2O. We've got a total of 6 oxygens and 4 hydrogens over here, so that's why we have the 3 as a coefficient in front of the oxygen, and a 2 is a coefficient in front of the hydrogen. So now let's take a look at water. The heat of formation in this table here from the elements, right there, the enthalpy value is equal to the enthalpy of water in the liquid state. This is listed as water, so by definition that means that it is liquid, not steam, not ice. And then we want to subtract from that the reactants, where we have 1 unit of H2 gas and then a half a unit of the enthalpy of O2 gas. So we're making water again from the elements, so it's water. Those are the products being made from the elements, hydrogen gas and oxygen gas. And then finally, for this guy here, anhydrite, this value here, the enthalpy, is the heat of formation for anhydrite, where anhydrite is the products, and then it is products minus reactants, where the reactants are. We've got 1 calcium, so the enthalpy for calcium, minus the enthalpy of sulfur, minus we need 4 oxygens altogether, so that's HO2, and we want 2 units of those so we can get 4 oxygens altogether. So these tables, there, and there, are giving us these heats of formation. Now, we don't want the heat of formation here. Here we're looking for the delta H of reaction, where we're looking at the formation of gypsum, not from elements, but from pre-existing compounds. Well, we can get this heat of reaction by taking the products, which is gypsum, and subtracting the reactants. So the the enthalpy of reaction is equal to the enthalpy for gypsum, those are our products, minus our reactants. And our reactants are the enthalpy for anhydrite minus 2 times the enthalpy for water. Now, if we use the heat of formation for all of these, all the elemental components will cancel out. leaving us with just the phases that we are interested in. So now we can get the heat of reaction by summing all these from the table. Let's clear this, and we'll make a little extra space by getting rid of this table here. So for the heat of reaction, we'll just rewrite this again. The heat of reaction will be the heat of formation for gypsum minus the heat of formation for anhydrite minus 2 times the heat of formation of water. And from these tables, notice that this is in joules per mole, so we need to divide this by 1,000 if we want to compare it to this, or multiply that one by 1,000. We'll do everything in kilojoules. So for gypsum, this fellow here is minus 2022 kilojoules per mole. From that, we will subtract the negative value, and that is minus 1434 kilojoules per mole, and then minus 2 times, well, we've erased it. If you play back the video, you'll see that it's minus 285, well, 0.8. We should probably round up to 286. So if we carry through the decimals in the calculation, we should get a total sum of minus 16.86 kilojoules per mole. So this is the heat of reaction for taking anhydrite, CaSO4, reacting it with 2 units of water, 2H2O, to get 1 unit of gypsum, CaSO4 dot 2H2O. So that is the heat of reaction for this thing here. It's not in the tables, but we can get it from the tables by taking the individual heats of formation. Why can we do this? Well, this is Hess's law. But Hess's law comes with a caveat. The reason we can do that here to get this number of 16.86 is because all of these values for delta HF are from the elements. This is from the elements here. We're forming anhydrite from the elements here, and we're forming water from the elements here. If we were forming anhydrite from the elements and water from the elements, but let's say gypsum from the oxides, then we'd have trouble because not everything would cancel. But because everything is in the same units, everything is a heat of formation of elements, then we're able to add these equations together and get this net result for the heat of the reaction. So this is the heat of this reaction. It now has nothing to do with the elements per se, even though the elements went into the calculation, but it's the heat of reaction that we would get from reacting anhydrite with water to get gypsum. That heat is negative, so that means that this reaction is exothermic. If we react anhydrite with water to make gypsum, there will be heat that will be released. Or by the converse relationship, if we put heat into the system, 16.86 kilojoules per mole of gypsum, then that's the amount of heat that would be required to break these two things apart and make anhydrite and water. So you can think of this going in either direction. We just happen to look at it this way, where for the reaction we're making gypsum rather than dissolving it. Anyway, that is an example of Hess's law, and the power of it is that we can take something like Roby et al., their 1979 list of thermodynamic properties and be able to take hundreds of listings and turn them into thousands and thousands of possible reactions. Any kind of imaginable reaction that you can imagine, so long as the data are in here for the elemental components, you'll be able to figure out what the heat of formation is for that reaction. In another video, we'll take a look at the same thing for Gibbs free energy of formation. We could play the same kind of games with Gibbs free energy as we did with delta H. Hess's law is usually expressed as a way of looking at the heat of reaction, but you can do it for any state variable. So delta S would work, and also delta G, and delta G is very powerful because we can compare the Gibbs free energy of the right side compared to the left side, see which one has the lower Gibbs free energy, and then make predictions about what is stable.